Hello AP Chem, this is Mr. Koker, and I do have the Chapter 13 Equilibrium PowerPoint ready to talk about. A little bit slow getting this one posted because I had to make it. Some of these in second semester I didn't have made from last year. So, Chapter 13 is on equilibrium. So, we talked about kinetics in Chapter 12. Took a week and a half on that. We're going to take about 9 class days on this one, although one day will be spent, at least part of it, talking about the kinetics lab. If you think about what we learned in kinetics was that reactions going in a particular direction have an activation energy and then they form products. If you take that same reaction energy idea, reaction profile idea, and then go in reverse, you could imagine that the products could collide, go over the activation energy hump and make reactants. So we're going to be talking about reactions going in both directions. This graph here illustrates what happens over time in a particular system where you reach an equilibrium. Your reactants get used up and the forward reaction slows down, your products get formed, they increase in concentration, and the reverse reaction speeds up. Well, at some point, the forward reaction and reverse reaction become equal. When they become equal, there is no longer any change in the amount of reactant and products, and that's called equilibrium. When a forward and reverse process are occurring at the same rate, you have a dynamic equilibrium. So all, nothing, or some. So until now, we've usually looked at reactions as either this reaction doesn't happen or this reaction happens until everything is used up or the limiting reactant is used up and then it stops. But we need to kind of adjust our thoughts to realizing that all reactions can go either forward or reverse. Anything that you can do in the forward direction, you can do in the reverse direction. So if we now open our minds to the idea of reverse reactions, then we're ready to start talking about equilibrium. So reactions that we've previously described as occurring or as not occurring at all actually only occur to such a small amount that we don't we say the amount that it goes forward is negligible, and so we say it doesn't occur at all. But in fact, it's occurring to a very minuscule amount. And that's because the forward reaction is very slow compared to the reverse reaction. So as soon as the forward reaction maybe makes a little bit of product, the reverse reaction is so fast that even at a low concentration, the reverse reaction reforms it back into reactants. And so at any particular time, you have very little product. So one way of describing that would be to say the reaction lies to the left, that reactants are favored over products. So at equilibrium, you're going to have a lot of reactant and very little product. Reactions that we've assumed to go to completion, and we do all of our stoichiometry and things like that based on reactions that go to completion, are really just reactions where the forward reaction is much faster than the reverse. We could say the reaction lies far to the right. The products are favored over reactants. Since the reverse reaction is so slow in comparison to the forward reaction, you end up with a lot of product, or virtually 100% product. But there are also some important reactions where your forward and reverse reactions maybe have similar speeds. And this can result in more of a mixture of similar amounts of reactants and products forming at equilibrium. And at this equilibrium, maybe you have some reactant and some product, similar to this graph here. You have a certain amount of reactant and a certain amount of product. The reactants haven't gone to zero and the products haven't gone to maximum. You've reached what's considered to be an equilibrium where you have a constant amount of reactants and products. So all reactions can be considered as equilibrium, although reactions that we generally refer to as occurring not at all are really just occurring equilibrium-wise to such a small amount that we don't really need to pay any attention to it. And then reactions that we say go to completion are really still equilibrium reactions. It's just the reverse reaction is so little compared to the forward reaction. So the equilibrium condition is talked about in 13.1. As reactants are used up, the forward reaction slows down. As products form, the reverse reaction speeds up. So at some point, you're going to reach a case where the forward and reverse reaction are occurring at the same rate. And once you've reached that point, the concentration of reactants and products are not going to change. Now, at the submicroscopic level, if we could see what was happening between the molecules, we would still see reactions occurring. It's just the forward reactions and the reverse reactions are happening at the same rate. The system is at equilibrium, but it's a dynamic equilibrium where reactants and products are continually changing place. Just the rate is the same in both directions, so you don't see macroscopically any change in concentration of either reactants or products. Now, to dive into this a little bit deeper, let's look at the reaction between water vapor and carbon monoxide in a container. If this is a closed system, and that's important, I probably should point that out, that equilibrium conditions need to be in closed systems. So they need to be, if it's gases, in a closed container. If it's aqueous, somewhat of a closed container, although a liquid is somewhat of a closed container if the stuff dissolved in it cannot escape and the liquid is assumed to be evaporating at a very slow rate. Then you can kind of consider an aqueous solution as a closed system as well. But anyway, we have equal moles of water and carbon monoxide in this container because we placed them in there that way. And then the forward reactions proceeding. So as the carbon monoxide and water vapors concentrations go down, the carbon dioxide and hydrogen's concentrations go up. Now in the left graph, we see the changes in concentration, and the dotted line, everything to the right would be once the system has reached equilibrium. Notice the graph is flat at that point. If instead of graphing concentration versus time, we wanted to graph reaction rates versus time, we would say the forward rate starts out fast, the reverse rate starts out slow, but at some point the forward rate is going to dip to the point where the forward rate equals the reverse rate. And once you reach that point, you've reached equilibrium. So let's go think about this system with the water and the carbon monoxide and the hydrogen and the carbon dioxide. Let's say we had the system at equilibrium and we've got the reaction going in both directions at the same rate, and then we inject some water vapor. So for a short period of time, that would speed up the forward reaction because now we've increased the concentration of a reactant. We're going to speed up the forward reaction. And for a little while, the forward reaction will be going faster than the reverse reaction. So we won't be at equilibrium for that small amount of time. But then eventually you reach a point where the reverse reaction catches back up and the forward reaction slows down enough that you reach an equilibrium again. So one way of really testing you on whether or not you understand the notion of this equilibrium and how it occurs would be to ask you which of the four species, water vapor, carbon monoxide, carbon dioxide, and hydrogen, is going to have a greater concentration than when you started versus which ones would be smaller than the original. So if we think about the addition of the water vapor, that would have increased its concentration, but then it goes down again when the reaction goes forward faster than it goes in reverse. But I would not expect the water vapor's concentration to decrease beyond or even down to the original value. We increased its concentration. It's going to go back down some as the reaction goes faster forward than reverse. But I would expect the water vapor after it's reached equilibrium again to still be greater than before we injected some water vapor. The carbon dioxide, on the other hand, on the other side of the equation, would have increased from its original value, because as the reaction was going faster in the forward than in the reverse direction, that was causing the carbon dioxide to build up, speeding up the reverse reaction until it caught back up to the forward reaction. Same thing with the hydrogen gas on the right. It's only the carbon monoxide on the left that would actually have a smaller concentration than originally, because remember, there was a period of time where the forward reaction was outrunning the reverse reaction, and during that period of time, more carbon monoxide was being used up than was being formed. Now you might think about that and go, wait a minute, why isn't the water less than it was before? Remember, we added water vapor. So water vapor maybe was at a certain concentration, we increased it, then the reaction began to go faster forward and reverse, and it went down, but it never goes down more than we increased it in the first place. So that's why water vapor will have a higher concentration than originally. So that's all just kind of a little mind problem there to get the idea of how does the concentrations of the reactants and products affect the forward and reverse rates, and try to tie your mind back to kinetics. So hopefully when you start thinking equilibrium, you won't just compartmentalize and not consider equilibrium as kind of a special situation related to kinetics, where equilibrium has to do with the forward and reverse rate being equal, but kinetics has to do with how we know how fast the forward and reverse rates are going to be. And so use your knowledge of kinetics to help you understand equilibrium. Now here's another case where we can kind of think about kinetics and equilibrium at the same time. This is the Haber process, and this is how they make ammonia for putting fertilizer on cornfields. Nitrogen and hydrogen making ammonia. But if you mix nitrogen and hydrogen gas at 25 Celsius room temperature, you're not going to see any ammonia formed. But the reason is not that there's that the equilibrium lies to the left, or that the reactants are favored over the products. It's that the kinetics of this reaction is just so slow that you never see any product forming. The forward reaction has a very high activation energy. The H2 single bond is actually a fairly strong single bond, and the N2 triple bond is very strong, and so it's very hard to break the bonds on the left to form the products on the right. Even though the products on the right may be favored, we don't see them forming at 25 Celsius, because in this case it's not equilibrium controlling the final amount, it's kinetics controlling the final amount. If you put this reaction under different conditions, which is what Fritz Haber figured out, was if you change the temperature, change the pressure, and use catalysts, you can get the system to reach equilibrium and to have an appreciable amount of ammonia formed. The problem is that at 25 Celsius and room temperature, room pressure, you just don't have a situation to where the reaction can go forward, even though the equilibrium might say that it would. Kinetics says it doesn't. All right, we're going to start getting into the algebra of equilibrium. And so this is your first exposure to the equilibrium constant, capital K. This is based on some experiments that were done on equilibrium systems. They noticed that there is this law of mass action. So in general, if you have JAs and KBs and LCs and MDs, you can derive an equilibrium expression or an equation for the equilibrium constant, capital K, which would be the products over the reactants, except that the concentration of the products are all raised to their coefficient as their exponent, and the reactants are raised to their coefficient as their exponent. And so Cl, Dm, Aj, Bk. So this is how we write the equilibrium expression, and if we plug equilibrium concentrations in for C, D, A, and B, and then do this math, we'll get a number that's called the equilibrium constant. So this formula, K equals the right side, is called the equilibrium expression. If you're ever asked on the AP test, write the equilibrium expression, they're wanting to write this formula, K equals products over reactants, and everything raised to their coefficient for their power. But the number for it, or the value of it, is called the equilibrium constant. Let's practice that. Let's write the equilibrium expression for 4NH3 gas plus 7O2 gas makes 4NO2 gas plus 6H2O gas. I haven't really mentioned it yet, but one way to recognize the difference between maybe a plain stoichiometry problem where you're assuming everything goes to the right versus an equilibrium reaction where you care about both directions is that we change our notation from an arrow to the right to an arrow that goes in both directions. So when you see that arrow pointing both directions in an equation, that's a good clue that you're doing an equilibrium problem. Okay, so the equilibrium expression here would be NO2 raised to the 4th power, H2O raised to the 6th power, NH3 to the 4th power, and O2 to the 7th power. So that's just how you would create the equilibrium expression. Then you would plug in numbers to get the equilibrium constant value. Let's get back to that Haber process. This is the Haber process, nitrogen and hydrogen making ammonia. Let's say that at 127 degrees Celsius, hot enough that we could start breaking some into triple bonds and some hydrogen single bonds, it was observed that the equilibrium concentrations were the following. NH3 is 3.1 times 10 minus 2 moles per liter, N2 8.5 times 10 minus 1 moles per liter, and hydrogen 3.1 times 10 minus 3 moles per liter. So our first question here is, can we find K? So our K expression is simply concentration of NH3 squared over N2 and H2 cubed. Plugging in our numbers, we get that the K is 3.8 times 10 to the 4th. Okay, just an important addition here. We made a big federal case over the rate constant having units and knowing what the units were for the rate constant. When it comes to equilibrium constants, we generally write them without the unit. It's just one of the idiosyncrasies of chemistry and how we do things, but you'd never show the unit for K. It has a unit. In this case, it would be molarity to the minus 2 because you have molarity squared over molarity times molarity cubed, but we generally do not show the unit for the equilibrium constant. No unit need be shown. Maybe when you take higher level physical chemistry classes, you'll understand why we don't need a unit for this. But 3.8 times 10 to the 4th. Second question. What would the K be if I wrote the reaction backwards? Well, I could write the K for this and put the numbers in and solve for it, or I could just recognize that writing it backwards simply flips the bottom to the top and the top to the bottom. In other words, it's the reciprocal. So all I need to do is take 1 divided by 3.8 times 10 to the 4th, and I would get the K value for this reaction. 2NH3 yields N2 plus 3H2 to be 2.6 times 10 minus 5. So that's an important distinction. Writing the reaction with one side and left side and right side defined does make a difference in how you calculate K. The reaction is still the same whether you write the reaction with the nitrogen and hydrogen on the left and the ammonia on the right. They're still the same reaction. But which one you designate as reactant and product will make a difference in the number for K and how K is calculated. So it's important that we define what do we consider to be our reactants and what do we consider to be our products, even though the reaction is reversible. And now one more part, let's throw in, what if we took the reaction that we started with and divided it by 2? 1/2 N2, 3/2 H2, 1 ammonia. Well, that you might see the reaction written that way, but dividing it by 2 simply means that all of the exponents are now half the size they were before. Instead of NH3 being squared, it's now the first power. Instead of N2 being 1, it's now a half, and H2 instead of being 3 is now 3 halves. Well, looking at that, multiplying by a half changes all the coefficients by a factor of 1/2, which would be the same in math as taking the square root. Remember, square root is raising something to the 1/2 power. So if I take 3.8 times 10 to the 4th, and I take the square root, I actually did not calculate this right. Let me real quick fix this. I took half of the k, not take the square root of the k. So let's figure this out. 3.8 times 10 to the 4th. That would be 38,000. Oops. Square root 38,000. $195. So I'm going to call this 1.9 times 10 to the 2nd. Okay, so fixing things on the fly. 1.9 times 10 to the 2nd is the square root of 3.8 times 10 to the 4th. So fixed it. Now, you can actually get to equilibrium from a number of different directions. There's an infinite number of initial concentrations you could start with, and then there could be an infinite number of equilibrium concentrations that could obey the law of mass action and equal the rate constant. So to illustrate that, let's look at 3 experiments, all based on this nitrogen, hydrogen, and ammonia reaction. Let's say you start with 1 molar nitrogen and 1 molar hydrogen. So you're starting with 1 molar of each of the reactants. Once you reached equilibrium, the nitrogen would have decreased to 0.921, the hydrogen to 0.763. Notice they decreased to different numbers because there's 3 hydrogens used up for every nitrogen. The ammonia would be up to 0.157, and you would equal, when you solve for the K value, 6.02 times 10 minus 2 at whatever particular temperature this happens to be at. K is a function of temperature. So you don't see the same reaction having the same K all the time. The rate constant can change with temperature. Nitrogen, let's say we started with 1 molar ammonia. Let's start with just pure ammonia. In that case, the reaction would proceed to the left until it reached equilibrium. The nitrogen would have increased to 0.399, the hydrogen to 1.197, the ammonia down to 0.203. But plugging those numbers in to the K expression, you still get 6.02 times 10 minus 2. And you could even start with some nitrogen, some hydrogen, and some ammonia. Let it shift to reach equilibrium and find your K is still 6.02 times 10 minus 2. So defining an equilibrium condition does not mean you define a specific amount of product and reactant. It means that your product and reactants have a certain ratio. Now we could look at this for gaseous reactions, not as moles per liter, but as pressure. If you recall, Pivner reminds us that PV equals nRT, or P equals N over V times RT, or P is really molarity times RT. So at constant temperature, R is a constant, T is a constant, P is proportional to molarity. P is proportional to moles per liter. So there's really 2 ways for gaseous reactions to write the K. There's the Kc way, which for the Haber process would be ammonia squared over nitrogen times hydrogen cubed, or the Kp way. So if you see this subscript P on K, it means use pressures, not moles per liter, and you would get P NH3 squared over Pn2 and pH2 cubed. So that's an alternative way to do an equilibrium problem, would be using partial pressures of the products and reactant gases instead of moles per liter of the product and reactant gases. Now, because P is not equal to molarity, but P is equal to molarity times RT, you can actually derive that the relationship between Kp and Kc, in other words, the number for Kp versus the number for Kc, is that Kp will be Kc times R times T, and you'd use the 0.08206 because you need moles per liter, and atmospheres because Kp will be in atmospheres, to the power of delta N, where delta N is the change in number of moles of gas. So in this case, N2 and 3H2, that's 4 moles of gas. 2NH3 is 2 moles of gas, so your delta N would be -2. So if I had the Kc for the ammonia reaction, I would divide it by RT squared to get the Kp for the same reaction. So far, we've generally been looking at gaseous equilibria, although you could also look at aqueous equilibria in a similar way. If you have everything are gases or everything is aqueous, it's called a homogeneous equilibria. You do see examples, though, occasionally, and AP likes to throw them in to see if you're paying attention, of heterogeneous equilibria. Heterogeneous equilibria means that your reactants and products are not all at the same state. Specifically, what do you do if you have a solid involved or two solids involved? Calcium carbonate solid yields calcium oxide solid plus carbon dioxide gas. Well, if I look at the K expression for this, I would say K would be concentration of CaO times CO2 over CaCO3. But if we think about it, solids actually have constant concentrations. So you can't make a solid more or less concentrated. A solid has solids are incompressible, and they have a certain density, which is their mass over their volume. If you convert their mass over their volume to moles over volume, you find that since solids have constant density, they have constant moles per volume or moles per liter or concentrations. So since the concentrations are not variables, they're constant, you could basically move them to the K side of the equation, and that's what we do. We make our math a little easier by not plugging in the moles per liter for the solids. We simply say that's going to be part of the K expression. So important thing to realize here that the K expression, the equilibrium expression, only includes gases or aqueous species, never solids or liquids, since solids and liquids have constant moles per liter. So Kc in this case would actually be CO2, just the moles per liter of CO2. And Kp would be the pressure of CO2 at equilibrium. You would not include the CaO and the CaCO3, they're solids. Now, another way we can use the equilibrium constant is the size of the equilibrium constant is actually an indication of whether products or reactants are favored at equilibrium. So when you see a K that's like really big, it means that that ratio of products over reactants is greater than 1, meaning products are more than reactants at equilibrium. So in other words, we could say the reaction favors products over reactants at equilibrium. But if you have a really small K, a K that's much less than 1, that's going to tell you that the reaction favors reactants and doesn't lie very far to the right. Now, let's say we have a mixture of reactants and products, and we want to know whether this needs to shift left or right in order to reach equilibrium. So we know our concentration of reactants, we know the concentration of products that we've put into the system, but we want to know, is this going to shift right to reach equilibrium, or is it going to shift left to reach equilibrium? Is the forward reaction going to be initially faster than the reverse, or is the reverse reaction going to be initially faster than the forward? Well, the way you determine that is you simply compare the ratio of the products to the reactants known as the reaction quotient, to the K value for that particular reaction. So here we have two capital letters, capital Q and capital K. They're very easy to get mixed up because you calculate them the same way. You put the products over reactants raised to their specific powers. However, there is a difference. K is only calculated using equilibrium concentrations. Q can be calculated using non-equilibrium concentrations. Q is simply your reaction quotient. It's your products over reactants. K is the value that reaction quotient should have to be at equilibrium. So Q is the more general application of that law of mass action where you take the products over reactants. K is specifically when you are at equilibrium, what is that ratio going to be? So let's use this idea. Nitrogen and hydrogen make ammonia. Let's say we have a K of 6.02 times 10 minus 2. Which way would the equilibrium shift if the ammonia started out as 1 times 10 minus 3 molar, the nitrogen starts out at 1 times 10 minus 5 molar, and the hydrogen starts out at 2 times 10 minus 3 molar? Well, the way to approach it is to find Q. Q is going to be 1 times 10 minus 3 squared over 1 times 10 minus 5th times 2 times 10 minus 3 cubed. Or in other words, Q is going to equal 1.3 times 10 to the 7th. Well, 1.3 times 10 to the 7th is a much bigger than the K value, which is 6 times 10 minus 2. So we're definitely not at equilibrium here. In fact, our Q is much too large to be at equilibrium. Q is much larger than K. So that is telling me that my product over reactant ratio is too large. I have too much product and not enough reactant in order to be at equilibrium. So in other words, the product is going to begin turning into reactant in order to get me to equilibrium. Or another way of saying it, the system will need to shift left. We'll need to use up some product and make some reactants to get our ratio correct so that we'll be in line with K. So the general way of thinking about this, if Q is greater than K, you need to shift to the left. If Q is less than K, you need to shift to the right. If Q equals K, it means you don't need to shift. You are at equilibrium and you're fine where you are. So let's take a look at calculating pressures and concentrations of reactants and products at equilibrium. We'll start out simple here. Let's say we have a system N2O4 makes 2NO2 and the Kp value for this is 0.133. So we're going to practice using Kp. So then at equilibrium, the pressure of N2O4 was found to be 2.71 atmospheres. What was the pressure of the NO2 at that equilibrium? So Kp, 0.133, is simply the pressure of NO2 squared over the pressure of N2O4, which is 2.71, plugging in and solving for the pressure of NO2, multiplying both sides by 2.71, take square root, you get the pressure of NO2 to be 0.6 atmospheres. So another one, kind of similar to that, but one you have to kind of do a little stoichiometry on. At a certain temperature, we have a 1 liter flask, and it contains 0.298 moles of PCl3 and 8.7 times 10 minus 3 moles of PCl5. Notice no Cl2 was mentioned, so we'll assume it has no Cl2 initially. It needs to reach equilibrium, so it'll basically shift to the right because without any Cl2 you can't go left, so it has to shift to the right to reach equilibrium. And once the system has reached equilibrium, you now find you do have some Cl2 because the forward reaction outran the reverse reaction for a while. You do have some Cl2. It's 2 times 10 minus 3 moles. So now let's find all three concentrations at equilibrium and the K value. So just remind ourselves, our initial concentrations, PCl5 was 8.7 times 10 minus 3 moles per liter. PCl3 was 0.298 moles per liter, and the Cl2 was 0 moles per liter. If you calculate a Q for those numbers, since Cl2 is 0, you'll get a 0, which means we need to shift to the right. Now, we shift to the right enough to make 2 times 10 minus 3 moles per liter of Cl2. So if you're following on this page here, start at the right, let's work left. 2 times 10 minus 3 moles per liter of Cl2. Well, that also means that the PCl3 goes up by 2 times 10 minus 3, or 0.002. So 0.298 plus 0.002, because you're also making more PCl3 if you shift to the right. PCl3 is now up to 0.300. The PCl5 has gone down by 2 times 10 minus 3 moles per liter because it shifted to the right and used up some PCl5. So 8.7 minus 2 is 6.7 times 10 minus 3 moles per liter. So these will be our final concentrations at equilibrium. And then the K value is just these numbers plugged into the K expression, 0.3 times 0.02 divided by 0.0670. I use the long form instead of the scientific notation. And we get a K value of 8.96 times 10 minus 2. Now, probably the most common equilibrium problem is one involving an ice table. You're learning it now for the first time, but you're going to use it probably for another 3, 4, 5 weeks. So these ice tables, they keep coming back over and over. So it's kind of how we do stoichiometry when we have equilibrium reactions. So let's say you only have initial concentrations of your reactants and products and you have K. They don't tell you any of the final concentrations, but you do have K. So the way we do these is we set up an ICE table. And ICE stands for initial change and equilibrium. Let's go back to that carbon monoxide water vapor reaction that makes carbon dioxide and hydrogen. Let's say that at 700 Kelvin, this has a K value, an equilibrium constant value of 5.10. And let's say that we put 1 mole of each reactant and product in a 1 liter flask. So we have 1 molar to start with of CO, water, vapor, carbon dioxide gas, and hydrogen gas. Now, plugging those into the K expression, if everything plugged in is a 1, and we have 1 times 1 divided by 1 times 1, Q is 1. So you are not at equilibrium with these initial values. But you write your ICE table as initial, or I. You can use I, because everybody knows I means initial in this case. And you write 1 molar under each reactant and product. Since Q equals 1, we'll need to shift to the right to make more product. So now I complete my ICE table by saying, okay, the initial is 1, 1, 1, and 1. My change is that if I shift to the right, I'm going to subtract X from CO, X from H2O, and I'm going to add X to CO2 and hydrogen. I'm going to make more CO2 and hydrogen, an X amount, and I'm going to make an X amount less, or use up an X amount of the carbon monoxide and water. So my equilibrium is going to be in algebra form 1 minus X, 1 minus X, 1 plus X, and 1 plus X. So then I plug those algebraic formulas in to the K expression. 5.1 equals 1 plus X times 1 plus X over 1 minus X times 1 minus X. Now you may be looking at that and going, oh wow, is he going to make me solve for X in that equation? That looks like something Mr. Ryan would make me do. Well, I'm nicer than Mr. Ryan. I'm going to show you a shortcut. Square root both sides. The top is 1 plus X times 1 plus X. That's square rootable. The bottom is 1 minus X times 1 minus X. That's square rootable. Look how much easier the math is if you square root both sides. It becomes 2.26 on the left equals 1 plus X over 1 minus X. Multiplying both sides by 1 minus X, you get 2.26 minus 2.26X equals 1 plus X on the right. Collecting like terms, 1.26 equals 3.26X. Dividing by the coefficient, X equals 0.387. Now, we're not quite finished. We've found X. That's where you'd stop in a math problem. But remember, this problem said find equilibrium concentrations for all 4 species. So let's go back up and do that. The carbon monoxide and the water vapor would be 1 minus X, or 1 minus 0.387, or 0.613 moles per liter. The carbon dioxide and the hydrogen would be 1 plus X, or 1.387 moles per liter. So, congratulations, just did your first ice table problem. Your first of many. So, our basic problem solving strategy is we start with a balanced equation. We write our equilibrium expression using law of mass action, K equals products over reactants. We list our initial concentrations. We plug it into Q and solve for Q and determine if Q is too small or too large and which direction we need to shift. We've got our I. Now we have our C. Our C is going to be plus or minus X's, maybe plus 2X or plus 1X or minus 2X or minus X or whatever the stoichiometry is for shifting right or shifting left. And then we combine the initial and the change to get the equilibrium concentrations, and then we plug those into the equilibrium expression and solve for unknown. And nice part about these, you can always double check your work. If you think you have the equilibrium concentrations, you should be able to plug them into the K expression and get the right value for K. So that's a good check on your math, is to always plug things in to see if you get the correct value of K. All right, looks like a lot on here, but I'll walk you through it. I'm going to show you another shortcut. There are times where you cannot take the math shortcuts, but there are two very common shortcuts that can be taken when you have equilibrium problems. One, of course, is that square root both sides. This one is what you can do when you have a very small K. Let's say that you have 1 mole of NaCl in a 2-liter flask, and that NaCl is going to decompose to make 2 NOs and Cl2. And you want to know all the concentrations of all the species at equilibrium. And your K is 1.6 times 10 minus 5. Well, I would say K equals 1.6 times 10 minus 5 is a pretty small K. Let's start with our initial concentrations. 1 mole in a 2-liter flask would be 0.5 moles per liter. And of course, no NO and no Cl2, so those are 0. To reach equilibrium, we'll obviously need to shift to the right. Q equals 0, so Q is less than K, so we have to shift to the right. We have to form product. So we're going to have minus 2x. Because of the coefficient 2, we're going to use minus 2x for the NaCl, plus 2x for the 2 NOs. Once again, NO is 2 NOs, and plus x for Cl2. So now at equilibrium, we're going to have 0.5 minus 2x for the NaCl, 2x for the NO, and x for the Cl2. Creating our K expression for this, we get 2x squared times x divided by 0.50 minus 2x, quantity squared. Now this is not one where we can square root both sides. However, since K is very small, a little misprint there, since K is very small, we can expect the shift to the right to be a very small amount. You will not have to shift very far to the right to equal K, because K is a small number. You won't need much product to make this equilibrium work. So we're gonna run with that idea. X is expected to be small. So now, if x is very small, 0.5 minus 2x is really going to be pretty close to 0.5. So if 0.5 minus 2x can be approximated as 0.5, now my algebra becomes much simpler. I can plug in 0.5 on the bottom instead of 0.5 minus 2x. Now, I've skipped a lot of algebra here, but you can put it on paper for yourself. Basically, K, 1.6 times 10 minus 5th, times 0.5 squared equals 4x cubed. So then you divide both sides by 4 and take the cube root. You get x equal to 1.0 times 10 minus 2. Now, let's go back and kind of double check our assumption. Our assumption was that the minus 2x could just be dropped off of the 0.50 minus 2x. Let's check to see if that assumption was valid. X is 1 times 10 minus 2. 2x would be 2 times 10 minus 2, or 0.02. Well, if I compare 0.02 to 0.5, it's only a 4% of 0.5. So what are we allowed to have as the difference between the approximated number and our substituted number? We're allowed 5%. So we just eked by on this one. 0.02 is 4% of 0.5. So we were only really throwing our math off by 4%. If we can throw it off by less than 5%, we're going to say the shortcut's allowable. So in this case, since 4% is less than 5%, the assumption is valid. The minus 2x is negligible. You can drop it out of the equation. You can do your math without the minus 2x in the formula, and we got away with it. So NOCl, if you assume the minus 2x is negligible, you would say that the final molarity is still 0.50 because it's still the same value that you started with because you didn't subtract anything. Now, if you want to be a little more upfront about it, you could say 0.48, 0.50 minus 0.02, 0.48 molar. The equilibrium for NO is going to be 0.02 or 2x, and the Cl2 will be 0.01. Now, if you plug these values in, I think you will find that you get very close to the proper K value, 1.6 times 10⁵. And finally, our last section to wrap things up. Back to a little theory here. Le Chatelier's principle. Le Chatelier, Frenchman, he basically said that if you have systems at equilibrium and then you do something that upsets that equilibrium, this is the direction it will shift to get back to equilibrium. So Le Chatelier's principle is all about the direction of shift once you have an equilibrium, but then your equilibrium gets upset. It's important to remember here that on the AP test, they let you use Le Chatelier's principle to determine which direction a shift will occur, but it's not considered a valid explanation for why. So it's similar to like the trends in the periodic table. You can say atoms get smaller left to right, but you need to explain that it's because nuclear charge increases. So Le Chatelier's principle may give you the direction of the shift, but it won't finish the answer as to why that's the direction of shift. And so you need to be able to say in more detail what is the reason why the reaction shifts that way. So as I go through my Le Chatelier's principle examples, I will also be including the explanation. So let's get Le Chatelier's principle out in the open here. If a change is imposed on a system that was at equilibrium, the change that's imposed is going to mean you're not going to be at equilibrium anymore. So you were at equilibrium, but then a change happened. The position of the equilibrium will shift left or right in the direction that tends to reduce the change. So if the change made something go up, the shift will make it go back down. Now it's important to note here that the shifts never bring you all the way back to the original value. They bring you back to equilibrium, but they never cancel 100% of the change. If you think back to that example that we had with the water vapor being added way back here, what would happen if some water vapor was injected? This is an example of something that you could use Le Chatelier's principle to explain. If water vapor is added, the change is to increase the amount of water vapor. The shift should be to decrease the amount of water vapor. The forward reaction speeds up and the water vapor goes down for a while. But remember, when we came to our conclusions on which ones would be greater than before, the water vapor was still greater than it was before you injected some water vapor. So you never really went all the way back to where you were before. You got back to equilibrium, but your equilibrium did not have the same amount of water vapor. It had a little bit more than you had before. Okay, so let's look at changes in concentration. So just like that example, if you add a reactant adding a reactant is increasing the denominator, because reactants are in the denominator of the law of mass action. So increase in the denominator is going to mean your reaction quotient is going to go down. You were at equilibrium, Q went down, now Q is less than K, you need to shift to the right. See, that's a math explanation of why adding a reactant makes you shift to the right. Chatelier's principle says it will, this says why. Now if you remove a reactant, now you're decreasing the denominator, which is increasing the ratio of products over reactants. Now Q is greater than K, so you need to shift left to bring the products over reactant ratio back in line with K. If product is added, you are increasing the numerator. Q is greater than K, you need to shift left. If product is removed, you need to shift to the right. You can also do kinetics explanation as well. You could say adding reactant speeds up the forward reaction, and as a result, the reaction shifts to the right because the forward reaction will be greater rate than the reverse reaction. So you could use kinetics to explain it, or you could use Q and K as a way of explaining the shift. Now, another way to change concentrations and upset an equilibrium would be to change the volume if you have gases, because changing volumes changes the moles per liter. Or if you have an aqueous equilibrium, you might dilute it. Now, it's important to recognize these are only going to shift your equilibrium if you have an imbalance of moles on the two sides of the equation. Now, what I mean by an imbalance of moles, N2O4 makes two NO2s. That's an imbalance of moles. You have 1 mole of N2O4 on the left and 2 moles of NO2 on the right. So changing the volume of this system, a system where this reaction was occurring, would affect the equilibrium. It would stress the equilibrium. And Le Chatelier's principle would tell us what we would need to do. So let's say that at a particular temperature, I'm just going to make some easy numbers here. The K for that reaction was 1. And the concentration of NO2 and N2O4 were both 1 mole per liter. So Q tells us that 1 squared over 1 is 1, and K is 1 in this example, which I'm just making up easy numbers. So 1 equals 1, so Q equals K, so you're at equilibrium. This would be an equilibrium mixture, 1 mole per liter of both gases. So now, what would happen to this system if we get back to the right? Come on. Here we go. What would happen to this system if we cut the volume in half? Say we've got it and we push a piston in, or we push in the plunger of a syringe, and the volume is now suddenly half of its original value. So Le Chatelier would analyze this and say, okay, your lowering of volume increased your pressure. Increasing your pressure threw off your equilibrium, and so you need to shift left because 1 mole of gas will have less pressure than 2 moles of gas. Now, how could we explain it mathematically? How could we use Q to explain it? Well, Q would change because the moles per liter of each gas would now become 2 moles per liter instead of 1, because you have the volume, you would double the concentration. If we plug those numbers into the law of mass action, we get 2 squared over 2, which is 2. 2 does not equal 1. Q is greater than K, so we need to shift left. Well, that's the same thing Le Chatelier's principle told us, that we would shift to the left. But now we've explained it using Q values. Now, if you had equal moles of gas, or if you had equal aqueous species, because another way of looking at this would be, okay, I'm not changing the volume of a gas, maybe I'm going to add water, which is going to change the molarity of the products and the reactants. If equal moles of gas or aqueous species appear on both sides, you're not going to change the ratio. You may multiply the top by 2 and divide the bottom, or multiply the bottom by 2, but your ratio is still the same. It's only when you have a different number of moles of products and reactants that changing the volume of a gaseous solution or gaseous mixture, or changing the adding water to an aqueous solution will affect your equilibrium, because Q will still equal K. There won't be any shift. Now, what about adding a chemical that's not a reactant or a product? Let's look at some cases of doing that. Let's say we added an inert gas like helium to a mixture of, say, nitrogen and hydrogen and ammonia. Well, at first glance, you might think, well, adding helium raises pressure, so the reaction shifts in the direction that lowers pressure. But you need to think a little closer about why the reaction shifts. The reaction shifts because the concentrations change, not because the overall pressure changes. And adding an inert gas is not adding any reactant gas or any product gas. So the concentrations of the products and reactants are still what they were before the gas was added, the helium gas was added. So really, adding an inert gas has no effect on Q. Q still equals K. No effect. So adding an inert gas, they like to throw that in to see, do you really understand Le Chatelier's principle? So remember, adding an inert gas, no effect on Q, and as a result, no effect on the equilibrium. What about adding a catalyst? Catalysts speed up reactions. So you might say, well, it makes a forward reaction faster. So you're going to shift to the right because the forward reaction is going to outrun the reverse reaction. But the catalyst lowers the activation energy for both the forward and reverse reaction. And as a result, the reaction is still going the same speed in both directions. So a catalyst doesn't change Q, doesn't change K, so you're still Q still equal to K. Your equilibrium position is still the same if you add a catalyst. Now, if you weren't in equilibrium, the catalyst would get you to equilibrium faster, but the equilibrium ratio of products over reactants is still based on products and reactants, not on catalysts. So catalysts are a kinetics thing. Catalysts speed things up, but they don't affect whether products or reactants are favored. And then finally, what if we add a chemical that might react with one of our reactants or our products? Well, if it reacts with it, it's going to make its concentration go down. So let's say we have a chemical like oxygen that reacts with hydrogen to make water vapor. How's that going to affect the nitrogen and hydrogen ammonia reaction? Well, if hydrogen reacts with oxygen to make water, that's going to remove hydrogen from the reactant side. If you remove a reactant, the reaction shifts left. So think about it in terms of what does this chemical do to the concentration of my reactants and products? And then your shift should be based on that. Finally, temperature. We know that K is a function of temperature. So changing temperature changes K. Everything we've talked about up till now has been about changing Q, adding reactant, taking away product, changing the concentration by changing the volume, adding water, whatever. We've been changing the Q value, so Q then has to adjust back to equal K to get to equilibrium. This time we're going to change K. So we're at equilibrium, Q equals K, but then K changes. So Q is going to have to change to catch back up to K. Changing T changes K, so the equilibrium shifts in the direction that brings Q back in line with K. Now on the right side here, I've got two graphs. And these graphs not only show the activation energy for the forward reaction, they also show the activation energy for the reverse reaction. It turns out raising temperature is going to speed up both reactions, just like adding a catalyst. However, raising the temperature actually speeds up the reaction with the higher activation energy more than it speeds up the one with the lower activation energy. So it just has to do with Boltzmann's distribution and how it all works. But the higher activation energy is more affected by raising temperature than the lower activation energy direction. So if we look at an endothermic reaction, the forward activation energy is greater than the reverse. So raising the temperature is going to speed up the forward reaction more than it speeds up the reverse reaction. As a result, it's going to favor making some more product. So in other words, raising the temperature of an endothermic reaction shifts you to the right. Similarly, if you look at the activation energies for the reverse and forward reactions for an exothermic reaction, you can expect raising temperature to shift you to the left. Now, if you take Le Chatelier's principle, the way to apply it would be treat heat as a reactant for an endothermic reaction or a product of an exothermic reaction. Treat it like it's a chemical. In an endothermic reaction, you put in heat. In an exothermic reaction, you get out heat. So if heat's a reactant and you raise the temperature by adding heat. If you add heat, you add a reactant, which causes you to shift to the right. Raising the temperature of a reverse reaction is adding heat to the right side of the equation, which shifts you to the left. So you're basically getting the right answer using Le Chatelier's principle, but it's better to understand deeper why that shifts it. It shifts it because it changes K. Raising temperature makes the K of an endothermic reaction larger. Raising temperature makes the K for an exothermic reaction smaller. And that's why you get the shift you get. Okay, that was a lot to throw at you at once, so hopefully you've digested all of this for Chapter 13 and are ready to start the homework.